Hey, welcome everyone. It looks like we're at the top of the hour and coming to the end of the conference. So thanks everyone who's been sticking around for 3 days or 4 days for those who started on Sunday. My name is Mike Gilliland from SAS, and I'll be the host or the chair for this final practitioner track session on the topic of probabilistic forecasting with Pyro, and presented by Edwin Eng and Fritz Obermeier. Edwin Eng is a senior data scientist at Uber and leader of a data science team that builds forecast models to support strategic decisions and optimal investment for marketing. Prior to Uber, Edwin was building cutting-edge statistical and predictive models at PayPal and 10X Commercial. Edwin received a Master of Science in Financial Engineering from UCLA Anderson School of Management and also holds an MS in Statistics from UCLA. Fritz Obermeier is a former senior research scientist at Uber, where he led engineering on the Pyro probabilistic programming language. Fritz is currently machine learning fellow at the Broad Institute of MIT and Harvard, where he continues developing the Pyro language with a new focus on biology applications. So let me now turn it over to Edwin and Fritz.
Hi, I'm Fritz. I'll be giving the first half of this talk, and Edwin and I will tell you about two tools for forecasting. Pyro is a low-level library for forecasting, and then Orbit is a higher-level library on top of, built on top of Pyro and PyStan for probabilistic forecasting. So let's start with just an overview of the context of what Pyro is. So Pyro is what's called a deep probabilistic programming language. It's a probabilistic modeling language that incorporates deep neural networks. We open sourced Pyro in 2017 from Uber AI Labs. And then in 2019, Pyro was adopted by the Linux Foundation. So now it's a collaborative project among multiple companies and institutions. We were really surprised after it was released in the number of people who built things on top of it. We found that Pyro is being used by both machine learning researchers to catalyze new research in methods, machine learning methods, and being used by practitioners in applied sciences. We also saw that Pyro is being used by a lot of companies, both large corporations and startups. Universities use Pyro to teach probabilistic inference in classes. And we've had a lot of contributors, over 100 contributors at this point. And we've also built a backend, multiple backends, one backend on Facebook's PyTorch and one backend based on Google's JAX deep learning libraries. Okay, so just now that we've seen some context, here's how the first half of this talk will be organized. First, I'll explain what deep probabilistic programming is, and then we'll go into how Pyro in particular implements deep probabilistic programming. And finally, I'll go over a brief example of how to use Pyro for probabilistic forecasting. And then Edwin will tell you more about Orbit in the second half of the talk. Let's start with what a probabilistic model is. So a probabilistic model is a way of expressing probabilities joint probabilities among multiple unknown variables. We call these random variables, by just declaring that each of those random variables is distributed according to some distribution and somehow linking these distributions together. And we can write that either in textual form on the left or in graphical form on the right. In the graphical form, the arrows mean that the parameters of a distribution of one random variable depend on other random variables. Here we see that X depends on these mu and sigma variables. We also distinguish between, in the graphical form, the shaded nodes, which denote observed data, and the empty nodes, which denote latent variables. In particular, the purpose of probabilistic inference, the goal of probabilistic inference, is to infer joint distributions over the latent variables conditioned or consistent with observed data. So this is a super simple probabilistic model. Another motif that often comes up in probabilistic models is repeated random variables. Of course, we seldom have a single datum. We usually have data, and these data, each row of data, say, or data point, is independent and sampled from a single distribution. And the naive way to draw this in graphical form would be to draw multiple nodes. But because this pattern occurs so frequently, we draw this in probabilistic graphical models as a box or rectangle, and we call this a plate. There's usually a subscript on the plate that denotes how many times the node or multiple nodes inside the plate is replicated. That's really important for deep probabilistic programming because we're going to do all of our probabilistic inference on GPUs and multi-core machines where we want to parallelize over multiple nodes. Probabilistic models are useful for a number of reasons. One is that they're great at allowing domain experts to express prior knowledge about particular problems. Another is that they're good at handling noisy data. They're good at fusing different data types, different data sources. You have two different data sets. They have different size. They're on totally different aspects. But it's really easy in probabilistic graphical models to just create different parts of your graph that incorporate different types of data. And they can handle uncertainty, especially uncertainty in the posterior estimates of these latent variables, these unknown variables. Another ideological advantage of probabilistic modeling is that they separate the modeling from the inference. We think of modeling as sort of a knowledge representation act and inference as sort of a computational act. And we can have different, we can wear different hats on different days. And one day we can think mostly about modeling and whether our model makes sense and is scientifically founded or founded by the problem at hand. And then on another day, we can think about getting our models to actually train quickly, and we can think about low-level programming. But it really separates those two acts, and then we can focus on either of those. And finally, latent variable models, these probabilistic graphical models with unknown latent variables, are often more interpretable than purely black box models, for example, pure neural networks or pure regression. I guess we could look at these coefficients in those models, but in probabilistic graphical models, we can learn both the posterior values of these and the distributions over these latent variables and inspect them. So next, I'm going to give you a brief history of the last, say, 20 years of probabilistic machine learning. Around 20 years ago, these models that people worked with were usually Bayesian networks. That is, these probabilistic graphical models with plates that we've seen so far. There were a few different inference algorithms around at that time. One of the most popular was Markov chain Monte Carlo. Markov chain Monte Carlo is great because it works on almost any probabilistic graphical model. There are very few model restrictions. However, it can be very slow to converge, and it scales poorly with large data sets. There were also, 20 years ago, popular variational inference algorithms, but these algorithms, inference algorithms, were restricted to conjugate models. That is, particular classes of a few different probability distributions or pairs of probability distributions that worked well with each other. That means that if you wrote down a random model, it probably didn't have a variational inference algorithm that was easy to apply to that model. And then deriving a new variational inference algorithm involved a lot of tedious math, often months of math before you could get a good inference algorithm. There were also custom inference algorithms like Kalman filtering that are super fast, but they're fragile, and even small changes to models, probabilistic models, often broke these algorithms. For example, if you introduce a nonlinearity, it might mean that the algorithm no longer works or requires a lot of changes. In the next decade, we saw the rise of deep learning. Deep learning had a number of advantages over probabilistic machine learning at that time. For example, it could run on, deep neural networks could run on GPUs. These massively parallel processors allowed people to train models with many more parameters and handle larger data. Additionally, deep neural networks were usually trained with stochastic optimization techniques. And these techniques are compatible with data subsampling. That means if you have an enormous data set, you can subsample into mini batches and train on little mini batches at a time so that your entire data set can be larger than fits in memory. And you only need to look at a little bit of it at a time. That allowed people to scale up to a huge amount of data that couldn't even fit on a single machine. Another technology that was really nice in deep neural networks, or leveraged by deep neural networks, was automatic differentiation. And this is just a sort of a symbolic computation technique, but it allowed people to avoid having to spend weeks or months hand deriving derivatives and gradient computations on paper or marker board or Mathematica. Because people didn't need to focus, because researchers didn't need to focus as much on math, they could perform more experiments and iterate on better models, and it really accelerated the rate of new architecture development in deep learning. And finally, it shouldn't be neglected to say that software engineering really played a big role in the deep learning, in the rise of deep learning. In particular, whereas a lot of the earlier machine learning research consisted of single papers or single isolated systems, the deep learning frameworks that large companies invested in often collected many of these papers into machine learning platforms with comprehensive tests and documentation and a lot of work to get these tricks to work together. In the next decade, people tried to look at, in the 2010s, people tried to look at combining these two paradigms, the paradigm of probabilistic graphical models and the paradigm of deep learning, where people try to train deep neural networks. And there are a couple of ways that people have combined them. One is to simply incorporate deep neural networks into models, that is, to create probability distributions that are very high dimensional and have thousands or millions of parameters. And another is to apply, that it's not quite visualized in the slide, but is to use deep neural networks also for inference. There are a few tricks that really help this research program go forward. One is the adoption of automatic differentiation, that trick from deep learning into probabilistic modeling. And this allowed people to replace their conjugate, remember those very restricted conjugate models, with what's called black box variational inference. So it alleviated a huge amount of tedious math from variational inference. Another was the realization that there's a stochastic variational inference method that's compatible with data subsampling, just like the deep learning subsampling methods. That means that people could apply their probabilistic inference algorithms on like huge data that didn't fit in memory or on a single machine. And finally, there was this realization that if you look at a particular deep neural network architecture called an autoencoder, if you look at autoencoders in a clever way, you can view them as variational probabilistic models and inference algorithms. So here I have a picture of a variational autoencoder. And variational autoencoders kind of changed the deep probabilistic machine learning field, because they allowed nearly black box inference and they could scale with data. So let's look at this variational autoencoder in a little closer detail. Mike, can you remind me when we're at halftime? I don't remember what time is halftime.
Sure, we're just 14 minutes in, so you're good.
Okay, great. So here we have an autoencoder. An autoencoder takes a large piece of data, compresses it through a trainable neural network down into a smaller embedding, and then tries to recreate the large piece of data from the embedding. These are trained by training on multiple input-output pairs to try to reproduce the output. And they're good for dimensionality reduction. Probabilistic machine learners researchers realized that you could add some stochasticity in a couple layers here. And then you can view these as not just bottleneck neural networks here, but actually as highly parameterized probability distributions. In fact, we can view these as a pair of probabilistic graphical models. The decoder model is like a generative model. It takes a low dimensional embedding random variable and runs that through an expanding neural network to create some observed data. And an inference model, what we call amortized inference, does the opposite. And this is exactly what the purpose of probabilistic inference is. It's to infer the random variables from observed data. The next advance beyond variational autoencoders was to widen the class of probabilistic models from simple neural networks to highly expressive graphical models, both for the encoder and decoder of these kind of VAE-like probabilistic programs or probabilistic models. The probably most expressive way of expressing probabilistic models is through a bespoke language. And this had been done in what were called probabilistic programming languages. In probabilistic programming languages, we express a model through a program that looks kind of like a sampler. This program has what we call sample statements representing latent variables. It has what we call an observed statement representing observed nodes, but it can also use the control flow of, say, this is embedded in the Python programming language. We can use control flow to express other structures. And we can actually have conditionals that don't even have an analog in graphical model form. And we've all written very large programs, and we realize that you can write, very complex probabilistic models if you use all the tools available in programming languages. We can leverage modularity and code review and all these great tools from programming. So here's where we are today. There are a number of deep probabilistic programming languages that combine deep neural networks, probabilistic modeling, and these expressing of those probabilistic models as programs, for example, in Python. The three that are on this, the three deep probabilistic programming languages on the slide are all based in Python. They're all based on deep learning frameworks that are implemented in Python. So the system I work on is Pyro, which is based on PyTorch. And I also work with the NumPyro developers who base theirs on what's called Google's JAX deep learning framework. And then Dustin Tran at Google has a deep probabilistic programming language called Edward, which is built on top of Google's TensorFlow. And in the last 5 years, there have been a number of important advances in probabilistic machine learning. And these are really important for actual, like getting inference to work on actual problems. And we've built those into these probabilistic frameworks. Okay, so now I'm just going to quick run through what Pyro syntax looks like. So remember, in probabilistic programming, we express probabilistic models as programs. So Pyro extends the Python programming language with a few different primitives that we can use in our programs. One of those is the sample primitive, and this line here basically says sample X from a Bernoulli distribution with this parameter of 0.5. We wrap that in a Pyro sample statement just to make sure that Pyro can record things about it. We give it a name, so Pyro can record things about that and kind of control the sampling of randomness. But importantly, in your probabilistic program that you're writing, the result of this sample statement is a tensor. This outputs an actual like numerical object. It's not some symbolic random variable object. It's just like you had sampled something from a Bernoulli distribution. We also have an observe statement, and this is how you express those shaded nodes in graphical models when you say there's a random variable y, but I know what it is. It's actually data, and it should be distributed according to some particular distribution. This is important to have in the language because that can give us information about, say, an upstream parameter x. Right? We can say if I know data should have been distributed according to this, that gives me information about x. We also have in Pyro a way to declare learnable parameters. This statement is a param statement. That's kind of a notion from what's called differentiable programming, where you write programs with holes and let some learning algorithm fill in that hole with a value that matches data. In Pyro, the parameters need to be provided with an initial value. This is only read the first time the parameter statement is called, and some kind of constraint, because constraints are really useful. Constrained parameters are very useful in probabilistic programming. The final piece of syntax we have in Pyro is what's called a plate that represents those boxes for repeated elements. And we have a plate that looks a lot like a Python for loop, but we also have a vectorized plate that looks like a Python context manager statement. And that's really important so we can parallelize and run on GPUs and get really fast speed ups by parallelizing. Okay, so now that we have these three statements in Pyro, or these primitives in Pyro, we can now construct probabilistic models just as Python functions. So here's a probabilistic model that inputs some data, it declares a parameter P, it then samples a random variable whose parameters depend on that parameter P. We can have some control flow. So this you can't even express in a probabilistic model, a graphical model language, because this node, what's called the obs node, only exists for some values of C. So it's already more, this language is already more expressive than the naive graphical notation. And finally, you see that we can use helper functions within our models. That means we can have probabilistic models that depend on other probabilistic models as code. And that means we can break our really complex probabilistic models into different components. Maybe we can share, those components between different people or different teams. Okay, so next I'm going to tell you about using Pyro for forecasting. So here's a big, here's a model. I don't want to go into the particular code, but let's just say it's a model with about 8 lines of code. Okay, so this is using Pyro's forecasting package. Pyro is a very general probabilistic framework, and in Pyro, we've written a forecasting framework where you can write custom forecasting models and have custom inference. And that's based on variational inference. That's based on that variational autoencoder technology that we saw earlier. Later, Edwin will tell you about some forecasting, the orbit forecasting package, which is easier to use and doesn't require as much code here. But if you want to write really custom models, here's how you can do that with Pyro's forecasting submodule. So you can write a model here. Here it inputs some covariates. Once you've written a model, and this model, it does involve just Pyro sample statements and Pyro param statements. But once you've written a model, you can then fit it with one line of code. We just have what's called a forecaster, and you give it your model, your actual data, some these are things you want to predict, some actual covariates, and then some learning parameters. And these are passed to like a deep learning algorithm. Like the learning rate is just like a stochastic gradient descent learning rate. So this could take a few minutes, and then once you're done with that, you can generate forecasts or samples from that. Just by passing it new data and new covariates extended into the future, and you can generate any number of samples you want. We also have some, you can either use your own evaluation metrics, or we have some of our own evaluation metrics. It's really nice to express your code in Python, your probabilistic model, because then you can make small changes to your model and just rerun your entire loop. There's no like recompilation step or anything. So here's an example. This example is from some tutorials we have at pyro.ai/time. And that is using the model that we just saw. But I just wanted to go through some of the results just to give you like a qualitative idea of what we can do here. So here's an example of some pretty simple weekly forecasting of ridership in some Bay Area transit. This is the train system in the Bay Area. So let's say we look at I think 8 years here, and all at once we try to predict the ridership throughout the next entire year. So let's look at some iterations on a model. This first model is the model that we saw briefly on the previous slide. And here it just has a single trend. It's just a generalized linear model. With just one line of code, I won't go into the code, but it's just one line of code that involves like this Pyro sample statements and stuff. We can add, say, a seasonality component to that model. And we can see that if we evaluate using CRPS, we get a better fit. And even qualitative, we can see it's a better fit. But we can also do things in Pyro like add some Brownian motion. And that takes, I think, about 4 lines of code. We can add some Brownian motion in a plate. And that allows some kind of a local trend, allows the signal to drift. And we see that indeed that works even better. With just a couple more lines of code, we can change that Brownian drift with Gaussians to a heavy tail drift. This is actually using a Levy stable motion, which accounts for shocks much better. And we see that this has even better accuracy. Pyro actually has a lot of machinery for dealing with heavy tailed distributions, in particular student T distributions. And I think we probably have the best support for Levy stable distributions out there. We have some really nice auxiliary variable methods for Levy stable distributions. This is all single, univariate forecasting, but in these tutorials, we also show how to do multivariate forecasting with, I think, every pair of stations. And it still runs on a laptop pretty quickly. We can train on every pair of like 50 by 50 stations, thousands of time series simultaneously, and do forecasting on a nice joint model. Okay, so that's all I'm going to tell you about Pyro, and now I'll hand it over to Edwin Ng to tell you about a package that's built on top of Pyro.
Yes, so let me share some of my application of forecasting at Uber Marketing. So my talk will be divided into 3 parts. So we will go over some typical forecasting use cases. Then I will go over some overview of the forecasting methods we did consider. And finally, we will go over our in-house solution that we recently developed, namely rbit. Next. So the typical forecasting use case at Uber can mainly derive into 3: monitoring the key performance indicators, KPIs, budget planning, and also synthetic control, as known as the causal inference analysis. And then the budget planning, there we can divide into 2 subcategories: the attribution and the optimization. So let's go through it one by one. Next. So for the first use case, monitoring the KPIs, so the idea is that we have KPIs on different products from the riders, drivers app to Uber Freight for logistics, and also Uber Eats for food and grocery. So the idea here is that we want to monitor the health and the growth of the business through these KPIs. And also the KPIs could be different from market to market. For example, in early launch city, you want to focus on the growth and acquisitions, while in the mature cities, you want to focus more on the earnings and revenues. And this type of problem is very open-ended. The methods could be from very machine learning, black box, to a traditional statistical methods. The idea is that we model the predicted KPI, the predicted KPI as a function of some future covariates and some temporal dynamics. And then there are some examples of covariates, such as the holiday indicators, policy changes, and campaigns indicators. And there could be some continuous variables, such as the marketing spend and promotions spend. So this prediction process usually is measured, the performance of it usually is measured by accuracy. So that's pretty much for the first use case. Next. In the second use case, we have the budget planning. And in the first stage, we have the attribution. So the goal of this process is to try to help the marketers to understand the performance and efficiency of each marketing resource. So in part, this is similar to the first one that we want to model some KPI with some covariates of marketing resource. However, there are some additional requirements that we want to have some capability to decompose the prediction outcomes with respect to this covariate for each marketing resource. So a very simple visualization here, you can see we have total prediction for each time period, and then we want to predict the portion that is contributed by each covariate, such as the organic channel, different channels. So then we can use this as the reporting or learning purpose for budget planning. Next. Then if we want to take it further to make a super data-driven budget planning, we can do some optimization. Again, we will leverage the forecast process as a simulation engine, such that we can vary the spend as a different scenario and then project outcomes in each channel. And as you can see at the right-hand side, this is known as the cost curve or the response curve. Then the pre-optimization here is denoted as the red dots, and the post-optimization is denoted as the green dots. And in a pure KPI maximization, you can think of we are just moving the red dots outwards for the elastic response curve, while for the inelastic one, we just move the red dots inwards. There is an alternative to do the budget planning by budget minimization. So then we will use in this case, we will use the forecast process as the in the constraint. So we will say in our optimization process, we want our forecast has to hit a particular minimum threshold. Then we will minimize our total budget for a certain period of certain covariate. Next. Then for the third use case, synthetic control, this is also a very popular topic. So from time to time in marketing, we want to measure the lift and also the causal influence of the change of policy or or when we have a new campaigns. So many times A/B tests may not be feasible, and also sometimes A/B test is not valid due to the network effect. So the alternative is we run the treatment and control on the market or city level. Then we observe the treatment denoted by YT here, and the observed control denoted by XT. So the observed control could be some market outside the treatment. And then we also observe this metrics in the post in sequential way, and also they can be observed between the in the pre and post period. Then we denote the YT1 as the post period observed treatment, and also the Y hat 0 as the estimated counterfactual. So here we need to leverage the forecast process to do the estimation of the counterfactual. So there are many practitioners using different rates. Some of them use the forecast process. Some of them also leverage the dynamics of the covariates. I don't want to go for too much details, but this is the an abstract description how we leverage the forecast process. So finally, the lift and the causal inference can be derived by the sum of the delta between the YT1 and Y hat 0. And so that's pretty much of the framework. Next. So up to this point, I hope you guys have some understanding of the typical use cases of forecasting at Uber marketing. Now let's go over some typical forecasting methods we did consider. Next. So traditionally, we have the ARIMA, exponential smoothing, and Kalman filter. And recently, there is a Bayesian structural time series framework developed by Steve Dodds around 2014 at Google. And so this is a Bayesian implementation of a reduced state space model with some regression components. And this in part becomes famous because of it supports the another package, causal impact, to do the synthetic control analysis I mentioned. And then, of course, we have the Facebook solution profits. We have a lot of presenters here talk about the application and the details of the model. So I'm not going over too much on that. And there are other practitioners use Gaussian process and machine learning models to do the forecasting task. And finally, we recently developed rbit as an in-house solution for some of the forecasting use cases. Next. So before I deep dive into our in-house solution, I want to provide some overview of the state space models, as I think it is very helpful for me later on to explain what our in-house solution is. So state space model is popular in part because of its structural outcome. So in general, it is divided into two phases: the prediction phase, that we have a weight matrix multiplied with the some transition latent variables. And then in the transition phase, we have the latent variable updates by the the updates process of this latent variable is described by the transition matrix and the covariates of noise. So notice that ARIMA and BSTS is a reduced form of such framework. And also the exponential smoothing can be expressed in this framework too. This idea is advocated by Rob Haymond. He called this as the innovation state space models, namely the ETS, error, trend, seasonality. So the key trick to make such conversion happen is to use the transition to re-express the transition noise as a fraction of the observational noise. Next. So now let me go over what rbit is. Next. So rbit stands for Object-Oriented Bayesian Time Series. It is a package, contains a bunch of probabilistic time series model. It provides Bayesian regression components with a very flexible, customizable priors. It provides full Bayesian inference thanks to the APIs of Pyro and PyStand. And the models follows the state space form, so it has a structural outcomes. And also the package is designed with object-oriented, in an object-oriented way. So it is very extensible to new models development. Next. So some models in rbit, we have the LGT, stands for the local and global trend model. This is an adaptive homoscedastic version of our LGT package in R. So due to this change, it trains much faster. And you can see this as a hybrid model of combining an autoregressive component and an ETS triple adaptive form. So this idea exposed so this idea is similar to an idea exposed advocated by Slavik Snil in the early time. And then we have a more classical model called DLT, stands for the damped local trend model. This basically is a Bayesian implementation of ETS triple adaptive model with the damped trend. Some noticeable changes here is that we, instead of the normal distributed noise, we introduced the T-distributed noise to make it more robust to the outliers. We also provide a regression component, and also we have the deterministic trend option, so that people can do a detrend process together with the parameters estimation. Next. Now, here is some deep dive in the LGT structure. So again, it follows the state space and ETS formats. We have the prediction equations. We have the update equations. So one important change here is actually in the prediction equations, that in our trend, we include a fraction of local trend and fraction of the global trend. So you can see this this way. So in an extreme case, when theta is 1 and psi is 0, this basically returns to a ETS triple additive format. And on the other hand, if theta is set to 0 and psi is some value greater than 0, then it becomes a autoregressive style model with a power term lambda to describe some nonlinearity. So we find this format is very useful, and there is some improvement in the accuracy, especially in fitting the noisy data. So the update equation is pretty similar to the ETS. So next. And then we have the DLT, the damped local trend model. So this one is very similar to the ETS, except that now we provide a deterministic trend. And so, by the way, the user can opt out the deterministic trend. So there are a few options from, so we can set GT as 0, or there could be some linear trend, not linear trend, or logistic trend can be chosen by the users. And also we mentioned that there is a regression component in these equations. So we will talk about this a little bit later. Next. So the two models I introduced is in addictive form. And one simple way to convert into multiplicative form is through the natural log transformation. So that is pretty straightforward. One thing notice is that so when we do the log transformation, the regression coefficient now is the elasticity of the regressor. So this is very useful for interpretability when we do regression analysis. Next. So back to the regression, thanks to the power of the probabilistic language programming, now we can make the regression reusable and modularized as a component in the package. So the user can pick different priors, such as the lasso, reach, and we are experimenting horseshoe prior as well. And then a user can also specify a constraint like a strictly positive coefficient or strictly negative. Next. Now, back to some benchmarking the performance. So just a very quick overview. In backtest, we have several parameters to configure the backtest process. For example, like the number of splits, forecast length, incremental length, and the minimum train length. And also we have two types of backtest: expanding window and rolling window. So in the next slide, we will show you the expanding window results. So next. So we do some performance benchmarking on our model against some other popular model with some internal and external data sets. And in the internal ones, we have the Uber rider, Uber driver acquisitions weekly series. We also have the Uber Eats daily series. And then for the external ones, we have the M4 weekly and MT monthly. So all of these data sets contains multiple time series from 20 to a couple hundreds. So the numbers you see here is the simple average of the S-MAP obtained by each time series. And the number you see in the parentheses is the standard deviation. So notice that our model outperformed other benchmarking model with some margin, except that the M4 weekly Ceremas does a very good job. Next. So just show you guys a very simple demo code. So again, rbit is a high-level wrapper of Pyro. So we follow the scikit-learn style of a framework. So basically, we initialize a model, and then we just use fit and predict to get the training and prediction done. So here, I set the decompose as true so that we can look at the decomposition of the hidden states. And also we use the plot functions built in the package. Next. Because this is the a MCMC algorithm, and we have posteriors back in our estimation, so we want to do some diagnostic and visualization of the convergence status and also the relationship of our posterior samples. So this is some examples how we do the visualization and diagnostic. For details, please refer to the slides I attached here. Next. So here's an overview of the package design. As I mentioned, this is an object-oriented design. So the key part here is we try to separate the estimator and model, so that for the estimator, it try to deal with all the IOs of the prior injection and also the posterior extraction and some aggregation. And then for the model part, that is the place that take care of the logic of how we, the math and how we fit and predict them as a model. So this way, the model, for the developers, they can develop their model by just looking at the inheriting the base model class. Next. So in the end, I want to show you the contributors of Pyro and rbit. I want to say thank you for all of them. And also there are a lot of community contributors in Pyro. So we welcome to any future contributions and look forward to any suggestion from you guys. That's pretty much for my presentation.
Thank you, Edwin and Fritz. I want to open it up now for questions or comments. Please feel free to enter those in the chat or the Q&A box. We've got a few minutes here before the top of the hour. I know we also have George is here lurking. I don't know if he may have some final comments as well as we wrap up the session. Hey, one thing I want to bring out is my background is mainly in the consumer products forecasting area, weekly, monthly forecasting, that sort of thing. So, you know, that industry, that group of forecasting is almost exclusively looking at point forecasts. And in your work, are you focused mainly on building the models and the languages and so on, a lot of the theory behind this, or have you had a chance to look out in terms of really communicating these approaches to the industry practitioners out there who probably aren't nearly as statistically savvy as you all are?
So I can take this question. So from my experience, so as I said, like I use Pyro as a solution to solve a lot of practical problems in my daily work. So I mentioned the three typical use cases from like a forecasting that rely on accurate, measuring the performance by accuracy, versus there are some very heavy emphasis on the causal inference, like the synthetic control, and also for the optimization. So yes, I think does it answer your question? So I think basically we do look at the inference of the predictions.
Yeah, I think it's a really important direction. I know now it hasn't got a lot of traction among industry, traditional industry forecasters, at least in the industries that I've worked in. So, definitely encourage not only the theoretical work, but also, continuing to look at ways to, help bring this, bring this to the masses out there of the industry practitioners. Well, we do have a question from Madi. what is the advantage of forecasting with Pyro in comparison with SAS?
I don't know details about SAS. I can tell you though that Pyro, it's a very low level framework, and it allows you to write really customized models and incorporate neural networks and train on you know, to run on GPUs and train on a large amount of data. Yeah.
Yep. Good. I think we've had a couple other SAS people from the audience. They were willing to chime in. That's great. Do we have another question from Virginia? Thank you for the talk. I was wondering if you tried Orbit with M5 data and how it performed given the intermittency of the data. So have you tried Orbit with M5 data?
That's a good question. So I do use Orbit for the M5 data. So because M5 data is a little bit special, there are a lot of low volume in many series. And right now, package does not take advantage of the hierarchy of the series. So I don't think it's very comparable. So I think there are some other discussion in other sections saying that for that particular competition, it favors the machine learning style methods a lot because of this low volume series, and there could be some interaction between the series.
Yeah, I know one of our Pyro developers submitted an M5, submission based on Pyro, and that was able to take advantage of some of the hierarchy. And I think we could run on GPUs and train over everything at once. I think that the hierarchy wasn't as useful as we had hoped.
Yeah, I think if we have time to come back to work on this, I guess some idea like a zero inflated Poisson with some hierarchical cross learning. If we build this structure with Pyro, maybe there could be a solution. Yeah.
Great. We've got another question here from Oscar. I don't know if you can see it yourselves in the chat panel, but does the main benefit from Pyro-based forecasting models come the ability to infer the impact of changing one of the model inputs on the target variable? What are the other strong use cases?
Yeah, so I guess when you express a probabilistic model, that's naturally a causal model, and you can do causal interventions or just change covariates to perform like counterfactual queries. And I know a lot of people are starting to use probabilistic programming languages for like causal analysis and these kind of counterfactuals. I'm not sure if that's exactly what you're getting at, but that's one thing we're looking at. I'm doing a little bit of epidemiological modeling where we're trying to make counterfactual or compare different inputs using Pyro. But I really think the strength of Pyro is just having a ton of flexibility and being able to use neural networks for whatever you want.
Great. I see we've got Nikos just put a comment in the chat. You can see that it's pretty long. I won't try to read it.
So yeah, so my experience is that Pyro, because of using PyTorch at the back end, it is very compared to other language like Stan, it is very easy to debug and very easy to go back and forth with your model development by just focusing on the single language. So you don't need to switch the mode that you are working on, this Stan code with Stan syntax versus the Python syntax. So that is the advantage I think of. And also it favors people when they think of, so because many of the things use the PyTorch tensor syntax. So for people who get used to the deep learning thinking process, it's very easy to like try to, for example, like if I want to make my model expand one more dimension to capture maybe some other dynamics, maybe some hierarchical model, it's pretty easy to do that. Basically, you just extend a dimension in a matrix basis. Yeah.
Great. Hey, we're going to take one last one before we hand it over to George for a few closing comments. It's from Christoph in the Q&A. Great presentation. Many thanks. For the LGT examples, what are the differences between the Stan and the Pyro backend in terms of speed, accuracy, and so on?
That's a good question. So because in Pyro we use the VI, the variational inference, versus the PyStan we support the full MC. So if we want to look for the accuracy, then I think using Stan is the way to go, and also it has more robust distribution of the posteriors. However, that said, it runs much slower, and also Fritz mentioned that too. And also it's less scalable because Stan is you need to run it like a compile process, and then Stan is not prepared for like the huge tensor computation, versus Pyro is using PyTorch, so it has the capability. So that means once we extend this to a larger data set, Pyro will shine because of this tensor computation structure.
Great. Hey, I think we're about to wrap up. Just one last comment. Tao Hong has sent a message to everyone reminding that if you've seen any student presentations, please go in and do the reviews of those presentations for the student awards. And with that, George, can I hand it over to you for the closing remarks?
Thanks, Mike. Thank you, Fritz and Edwin, for another really strong practitioners session. Really enjoyed it. I just wanted to bring to your attention the practitioners conference that we are organizing, Len is organizing. I also wanted to encourage all practitioners to get more involved with the Institute. I consider practitioners an integral part of the Institute, and whoever's on the board knows my strong views on that. So please let us know what you need as practitioners. Do you need more than just the forecasting practice conference that we're doing? Can we do something more to, to serve your community as well as academics? I think it's integral that you're part of this institute. Please come forward with ideas. We are open to those, and we would like to do more. Having said that, just to thank everybody for participating, thank all the practitioners for participating, everyone for participating. I think it's been it's a success beyond expectation, let's say this, so given the circumstances. Thank you very much.